Hi everyone. I'm sure all of us know of or have at least heard of the world famous Statue of Liberty. It's one of the tallest monuments in the world and is located in the city of New York in the United States. And some of us who have had the opportunity to go to New York City have most likely paid a visit to the Liberty Island and took a look at this great piece of work. So, just to give you guys a little bit of history here, this statue was, in fact, a gift from the people of France to the people of the United States back in the year 1886. And so, this was sort of in recognition of the friendship that was established between the two countries back in the days of the American Revolution. So, so the guy behind building the statue was this French architect and sculptor, Frederic Auguste Bartholdi, and he was not alone. He, in fact, took help from this very talented civil engineer, Gustave Eiffel. And you actually might recognize this guy from his last name because he is the guy who actually built the Eiffel Tower in Paris. And so let's see what materials Bartholdi and Eiffel chose back then to build this statue. For people who do not know about this, it might come as a bit of a surprise here, just like it did to me when I first learned about it. This statue is in fact a huge copper sculpture, and the surface of this looked pretty much like the shiny surface of copper coins you see today. Just let me bring up a picture here. Um, so something like this. So in fact, somebody had the time to take a photograph of the Statue of Liberty, how it looks today, and sort of manipulated it in Photoshop or something, and um, just to give you an idea of how the statue might have looked back then when Bartholdi and Eiffel first built it. So it's pretty amazing how something like this became something like this with this mysterious blue-green color that it has today. And mind you, it's not a coating of paint or something that was applied on top of the statue, but it's something that happened to copper over years. And that's what we're going to look into today. But the statue is not all copper, of course. It's just copper skin, and just like we humans have a skeleton of bones underneath our skin, Bartholdi and Eiffel built a skeleton made of iron bars, and the skin, you might be surprised to know, is only about 2.5 millimeters thick, and as thick as two copper coins stacked up together, and that's how thick the copper skin is.
So the question then is, what exactly happened, to the surface of this statue for it to go from this really shiny copper finish that it had when it was first erected to this, what we see today, this bluish green appearance that it has? And the answer to that is actually the fact that copper reacts with oxygen and water in air and forms a variety of compounds over many, many, many years. And, the statue being surrounded by the ocean on almost all sides, one would expect the water content or the humidity levels in the surrounding air to be pretty high. And not only that, there is also a good amount of, say, carbon containing compounds like carbon dioxide and sulfur containing compounds like sulfur dioxide, sulfur trioxide, and even elemental sulfur for that matter. And these guys generally get released or generated when you burn fuel, like for example coal, and it being New York City, due to all the traffic and pollution, you would expect that these compounds, like carbon and sulfur containing compounds, also to be pretty high in the surrounding air. Um, so let's back up a little bit and look at the sequence of the reactions that most likely happened over many, many, many years, um, for the statue to turn into this bluish green appearance that it has today. So I'm sure you've heard of the concepts like reactions, reduction reactions, redox reactions, and even terms like oxidation states and oxidation numbers, and in your chemistry lectures. So I won't go into a lot of detail there, but Copper, specifically, as you might know, is a transition metal and it's an electropositive element, meaning in presence of, say, highly electronegative elements like oxygen and sulfur, copper, would love to give away electrons and go into positive oxidation states, meaning, and these guys, for example, oxygen and sulfur, and as you might know, are some of the most electronegative elements that you can find on the planet. I mean, they would readily, would love to grab electrons wherever they can to kind of fill or satisfy their valence shells and get into a happier electronic configuration or happier state. So, so copper actually can exist in two different oxidation states. It can give away one electron and go into a +1 oxidation state, or it can give away one more electron and go into a +2 oxidation state. So this is +1 and +2. So what happens when the statue is first exposed to air is that copper reacts with oxygen and forms this compound called cuprous oxide, which is Cu2O. This is also called copper 1 oxide because copper here is in +1 oxidation state and oxygen is in -2 oxidation state. So oxygen actually requires two different copper atoms, each giving away one electron to form this bond. And cuprous oxide is has this really pretty pinkish red color to it. And let me bring up a picture real quick. This is how it looks. And so once cuprous oxide is formed, let's go ahead and balance this here. So you have one copper and two coppers here, two oxygens and one oxygen here. So if we go ahead and get two oxygens here, so the oxygens are balanced now. Now you have four copper atoms here and one copper atom here. So if you multiply copper here with 4, so this reaction should now be balanced. So then what happens? Copper says, well, I can give away one more electron and go into +2 oxidation state. So in that case, cuprous oxide goes on and reacts with oxygen again and forms what is called cupric oxide, which is CuO. So in this case, copper is in +2 oxidation state, meaning copper in effect has given away two electrons and oxygen, as always, is in -2 oxidation state. So in this case, oxygen actually requires only one copper atom because this copper atom gives away two electrons. So it's enough for oxygen to form this bond. So that is cupric oxide. And in fact, this compound is black in color. And here's how it looks. Let's see how we can balance this reaction here. So on the right hand side, you have one oxygen atom for every copper atom. In other words, the ratio of copper to oxygen is 1:1. So we need to maintain the same ratio on the left hand side of the equation. So currently you have 2 plus 1, 3 oxygen atoms, an odd number of oxygen atoms, and you have two copper atoms, an even number of copper atoms. So to make the oxygen number of oxygen atoms even, let's multiply this here with 2, so that you have 2 plus 2, 4 oxygen atoms, and you have 2 times 2, 4 copper atoms. So the ratio now is 1:1, just like on the right hand side of the equation. So now you have 4 coppers and 4 oxygens on this side. So let's multiply on this side by 4, so that you have 4 coppers and 4 oxygens. So that's how this reaction is balanced. So another possibility is copper can react with elemental sulfur and give rise to what is known as cupric sulfide, and that is also black in color, just like this. So cupric oxide and cupric sulfide are both black in color and look like this. So at this point, you might think that, okay, copper gave away two electrons and got into a +2 oxidation state, and that probably is the most stable configuration in terms of its valence shell configuration that copper could get into. So you might say that, oh well, then the statue might have looked black in color at some point over this period of time, but that's not true because cupric oxide then goes on and reacts with carbon dioxide and water in air and forms this bluish green mixture of compounds, um, which are copper carbonate and copper hydroxide. And this has this bluish green color to it, and this is how it looks. Let's see. So so we are getting pretty close. I mean, this color here is pretty close to what we see on the statue today. So this mixture is a mixture of copper carbonate and copper hydroxide. So let's go ahead and balance this here. um, so you have two coppers on this side, whereas you have one copper on this side. So let's go ahead and add a multiplier of 2 here. So let's see if we are lucky in terms of how the other atoms are balanced. So you have two coppers, 2 plus 2, 4 plus 1, 5 oxygens, and 3 plus 2, 5 oxygens, and then 2 hydrogens and 2 hydrogens. So we are pretty good here. So cupric oxide can also react with sulfur containing compounds like sulfur trioxide in this case and water. As I said, sulfur containing compounds like sulfur dioxide or sulfur trioxide generally get released into the atmosphere when you burn fuel like coal or gasoline or any other fuel that has sulfur for that matter. So cupric oxide reacts with sulfur trioxide and water and forms this mixture of copper sulfate and copper hydroxide. And the ratio of sulfate to hydroxide in this mixture can vary. It can either be 1 is to 3, or it can be 1 is to 2, which means for every copper sulfate molecule you have 2 copper hydroxide molecules. So I'll leave it to you guys to balance these reactions. Um, but but these in fact are very well known copper minerals that you can find in various mines, copper mines across the world. And so, as you can imagine, copper being a reactive metal, like you saw how it reacts with oxygen and air, water in air, it's it's very difficult to find copper in its purest form. So what people do is dig out minerals that have sulfates and hydroxides or carbonates in them, and then try to extract copper in its pure form out of those minerals. So copper sulfate, for example, in by itself in hydrated form has this really pretty blue color to it. And let me bring up a picture real quick to show you guys. That's how copper sulfate in hydrated form looks. But the mixtures that I've shown here, where copper sulfate and copper hydroxide, they actually have a green, emerald green or bluish green color, just like that. So there you go. So it's a mixture of carbonates and sulfates and hydroxides, which is what causes the statue to have this bluish green appearance that you see today. Um, so the mixture of all these compounds, especially the carbonates, hydroxides, and sulfates that eventually form over many, many years, is often termed as patina. So the good thing about this patina is the fact that once a nice continuous film of all these compounds, especially the carbonates, hydroxide, and sulfates, forms on top of the copper surface, this film sort of protects the copper metal underneath from further corrosion. So it takes care of itself in that sense. So you don't need to add a protective film or a paint or a coating of paint on top of the statue to protect the statue from corrosion. So in the next presentation, I'll talk about what happened underneath the copper skin over all these years, the skeleton of iron bars that Bartholdi and Eiffel built back then. So see you next time then.